All right, so we've got one more example in this list where we've got a set of vectors and we want to know if it's linearly independent or not. Before we jump into the details, which are going to be similar to the previous examples, we're going to not, our approach is not going to change too much. I just want to make an informal remark that's more of a qualitative idea and is not precise, but I think it's helpful. Roughly speaking, the idea of linear independence is it's trying to capture the sense of a set of vectors not having any redundancy. What do I mean by redundancy here? Well, if you think of vectors as information to describe something, if you have some of the vectors giving the same information, then that would be kind of considered redundant. So with that line of thinking, the more vectors you have in a set, the more likely there is to be some redundant information among those vectors. Okay, so as your set gets larger and larger, it's kind of tempting to start to be suspicious that, maybe this isn't going to be a linearly independent set. Because again, another way of thinking about linearly independent sets is that if they're linearly independent, they're not too large of a set. Again, that's a really informal idea, but I think it's a helpful way to think about it, especially when we move forward and in future sections when we talk about bases for vector spaces. That's where these ideas really will come together. But for now, if we just think of linear independence as the absence of redundancy among the different vectors in a set, then the fewer the vectors, the less likely there is to be redundant information. So with that in mind, let's check if this set is linearly independent or not. So we'll start in the same way we did the previous examples. We'll start with the assumption that we've got a vanishing linear combination, which would look like this, right? For some weights, C1, C2, and C3. Okay? Now, what's that going to lead to? That's going to lead to the following augmented matrix. Okay, and then when you find the reduced row echelon form of that matrix, what you're going to get is the following. You'll get 1, 0, negative 3 halves, 0, and then 0, 1, 2, 0. Okay, this is just what you'll end up with. So when you go to write down your general solution, you'll have your C1, C2, and C3 will look like this. Your C1 will be 3 halves S, your C2 will be negative 2S, and your C3 will be S. And of course, if you choose a different parameter for C3, then you'll change the C1 and the C2 to reflect that. But this is true for all values of your parameter. I'm just going to say S is in the reals. Okay, what do we know? That means the set is not linearly independent, right? Because if we have a parameter, that means we're going to have a non-trivial solution to this linear system here, which means there's some non-zero values of C1, C2, and C3 that makes this vector equation be satisfied, which means the vectors are not linearly independent. Let's write down a specific case. So let's take S equal to 2, because that'll kill all the fractions in this vector, right? So if we take S equal to 2, then we'll get C1 is equal to 3, C2 will be equal to negative 4, and C3 will be equal to 2. And that'll tell us that this is a vanishing linear combination. 2, 4, negative 2, plus 3 times the vector 3, 1. Oops, I'm reading those backwards. I read this as a coefficient, but we actually want these as the coefficients. So we'll have 3 times the vector 4, negative 2, minus 4 times the vector 3, 1, and then plus 2 times the vector 0, 5. And that is going to give you the 0 vector. So now we have ourselves a vanishing linear combination where the weights aren't all equal to 0. So we can say that S is linearly independent or linearly dependent. It's linearly dependent. Okay, so that takes care of that. So like I said, the more vectors seems to mean that you have less of a chance of being linearly independent. And that if we were to go with that assumption, we would have been correct here. Okay, the next example is really, it's not that different. It's just the way that the question has been asked is a little bit different, right? So we aren't given vectors, not directly anyway. We're given a matrix, 3 by 3 matrix, and we're asked if its columns are linearly independent. Well, its columns can be interpreted as vectors, right? We've got three vectors if we break the matrix up into 3 columns. And you could ask the question, are those 3 columns linearly independent? So that's what we're going to answer. So we'll start in the usual way. Start by setting up your vanishing linear combination. And this will give you a vector equation. Okay. And that's got to equal the 0 vector. Okay, and what's that vector equation going to lead to? It's going to lead you to this augmented matrix. You're going to have 1, 0, 1, the first column, then the second vector, the third vector, and then the constant column. And if you row reduce this, again, I'll fast forward through the row operations, but if the row operations, or the Gauss-Jordan elimination method, will eventually bring you to this reduced row echelon form. It's actually that perfect reduced row echelon form where the ones come down at that nice perfect diagonal, and that's what gives you the trivial solution. So you end up with C1 is 0, C2 is 0, and C3 is 0. Okay, so in this case, that means the 3 vectors that we set up in this vector equation, so this vector, and this vector. So in other words, the columns of the matrix A, right? They are linearly independent. So the answer to this question that was originally asked is yes. So the answer is yes. Let's write it out fully. The columns of A are linearly independent. Okay, now what happened here? And of course, there's some work to be done here, right? As with all these examples, I'm skipping over the row operations, so I maybe making it look like it's less work than it is, but there is a non-trivial amount of work here to reduce this system. But what actually, let's look at the overarching themes. What happened? We started with the matrix A, and we were asked to if its columns were linearly independent. So in a sense, we took the matrix apart into its separate columns here and set up this vanishing linear combination. But then what happens when you have a vector equation like this is you end up putting those columns back together. And so what you have here, this is exactly the matrix A that we started with, isn't it? So what that says is that this augmented matrix, this is exactly the augmented matrix of the associated homogeneous system to the matrix A. This is nothing but the augmented matrix of the matrix equation AX equals 0. So if you're ever asked, are the columns of a matrix linearly independent, that's equivalent to saying, if you were to set up the associated homogeneous linear system, does it have only the trivial solution, right? In this case, it did. So the answer was yes, the columns are linearly independent. So this is an opportunity for you to shift points of view in a problem. So if you have a matrix and you want to know if its columns are linearly independent, that's the same as asking the question, does the associated homogeneous system AX equals 0 have only the trivial solution? And that's what this remark here is saying, okay? And you notice the language that's used. In this remark, it says the following statements are equivalent. Okay, that's a very commonly used phrase in mathematics. Whenever you hear that phrase, it'll be followed by a list of statements. And here's the essence of what that means. When you make a claim like that, if you write down a list of statements and say that they're equivalent, what you're saying is if one of those statements is true, all of those statements are true. But if a single one of those statements are false, then all of the statements are false. So in other words, they're all true under the exact same circumstances, and they're all false under the exact same circumstances. So what that's useful for is maybe you want to know if one of the statements is true, but maybe it's easier to check if one of the other statements is true. That's the setting in which you would use a fact like this. But in any event, this this remark is true, and for the reason that we just kind of outlined right now. If you go to check whether the columns are linearly independent, you're going to end up with this vector equation, which gives you this augmented matrix, which is equivalent to the associated homogeneous linear system, to the matrix that you started with.